Oh. Okay, I'm thinking if we can start at least this part. So the laser Macintosh doesn't have a USB thing. Good. Okay, not a problem. I still have the laser. Or not. I have the laser. I got it. Okay, I don't know if they started already, because they told me it's recorded. I don't know if it's... Hey, hi, Thomas. Okay, so maybe we can try, roll back in case they come back and say, oh, we haven't recorded anything. Okay, so.
I don't know, I don't have anyone to ask you.
Anyone has already tried to connect to the Wi-Fi, download everything, go to the GitHub of the project, of the workshop, see if it exists. It exists, actually. Okay, fine, perfect. Okay, then I don't have the power to change the slide, so I can fake it and you will see. Perfect. Okay, so as Daniele has already explained, this is a 1 hour or less long, probably with the inconvenience it could be 2 hours. No, I'm joking. It's just 1 hour of presentation about profiling methods, what they are, not exactly which profiler exists, but a taxonomy of the different type of profiler to better understand what are the kind of tools that we are going to use today. Okay, so I have to say click every time. Okay, who are we? So let's start presenting each other very quickly.
Okay. Hello, I am Sanne. I am Dutch and Italian. I live in England. I am mostly known, I am the technical lead for the Hibernate project. I am an architect at Red Hat, and I work on Quarkus as well. And yeah, very passionate about performance, so happy to be here.
I'm Francesco Nigro. I work for the service performance middleware team, long name. I'm a performance engineer in theory, an engineer. So I use profilers all day long, more than I wish, probably.
I'm Daniele Zonca, still a Red Hat company, senior software engineer, mainly looking at now serving technology on OpenShift AI, so try to enable artificial intelligence workload. We live quite close each other, and we work together quite often. And I did I'm being the beta tester of this presentation, so hopefully things are going to work well on Mac too. So.
Right now I've been already surprised by Mac, apart from the USB thing. Click. Great, so we already saw that, so we can move away. Okay, profiling in general, what they are, what type they are. So let's reach the source of truth, Wikipedia. So according to Wikipedia, there are different kind of visualization for profiling data, but about the profiler itself, there are tools and harness that are able to collect in different ways meaningful information from running application. So they are observer, let's say, and capable to collect data. There are different types, so you can see in the last 3 lines the different types, and they have event-based profilers, so in which there are events that are emitted, collected, and show up. You can have a statistical profiler that they have a kind of interval or frequency by which they can collect those information, or they can even not just collect, they can fire command to the application or their runtime or whatever in order to collect this meaningful information. And then we have the instrumentation kind of profilers. To be honest, we can use all of 3 for this workshop, but we will focus for the very first 2 types. Actually, the second type. Statistical are even called sampling profiler. No, makes sense. So, what's important? The key word about profiling is not that they are measuring performance. Performance is a word that doesn't mean anything, actually. Performance of what? You can have different kind of resources you should care about while you write your program, while you have to deploy your program. It could be memory, could be CPU time, it could be number of cores, it could be a lot of things. Recently, carbon consumption. There is a direct connection between, a proportion between CPU's usage and carbon and memory, but still is a separate kind of resource that you could be interested in. So profilers are there to show up different type of resources that you should get, you care about. Let's see if, well. Oh, okay, let's see if that works. We'll take 1 second. What means? The other side? Right.
You can plug to your laptop and then?
Okay. But yes? USB-C to USB. But for us is, we have just the HDMI and USB-C doesn't work. And with the USB, I can't project I can take the video in. Or if you want to, thanks.
No, the problem is that.
No, it's not Mac the problem.
No, the challenge is that he needed to plug directly the HMI to.
Yeah.
And that you don't have anything.
I have HDMI and an not working USB-C.
Or it seems not working.
Yes, I mean, it's Linux, it should work. It never be a desktop day for Unix. We'll wait 20 seconds for your patient, and then I will move on, so to not lose the momentum. Oh, don't worry, I will keep on. So, click. Okay, I already told that. So these are the kind of profiling type techniques. So let's move on. Why not profiling? Now, I mean, in every long, complex kind of presentation, we need some funny slides, you know. So in this case, these are the funny slides, but I invite you to try to classify yourself and the people around you without saying them this. What kind of engineer you are related, why not profiling? So maybe it's too complex. I mean, in general, it's very tiresome. You need to download tools, learn how they work. Probably they don't work most of the time. You don't have the right environment. You don't have a good machine. Maybe you need to set up the CPU frequency to be blocked. It's a mess. I won't do it. I'm too lazy. So let's move. Sometimes you don't want to know what you're going to discover. And it's very real. The more you are higher in your position in your team, sometimes you really don't want to know because it means more work, a lot most of the time. So better not knowing anything about it. Too many tools. I try to search about profiling on Wikipedia, Google, and there are Datadog people here. Okay, they try to sell me something. No, really, they made a great profiler, but it's their job. Basically, there are a lot of tools. Sometimes are good, sometimes are less good. It's not important. But the point is that there are so many. It's not easy to find it out where to start. So sometimes we stop earlier and say, okay, I won't do it. Too complex for me. There are no workshop for this. Sometimes I look at the code and know when it's slow. Or better, I presume I know that. And the too smartness thing, it's definitely a real thing. The more you know about your code, the more you tend to assume where the problems are. And that means that why should I profile? I know already where the problems are. Is the database or a DNS? No. Let's move on. And the reality is that whatever kind of category you belong, you should measure. It doesn't cost that much. And we already a scratch project to start with by the end of this presentation, so you will find out that it's not that complex to start. on this. And definitely it's fun. No, I hope it will be. You know, we have a wine there. No, we have no wine, but it will be fun by the end of the presentation because you will discover more about the dynamics of your system. There are certain type of companies that use a profiler not as a tool to improve the performance of your application. They are used with the new engineer, onboarding of new engineer, to make them to know the dynamic of the system, because they are holistic tool that can grant you a wide view of what's going on. And they are definitely useful to see how things are connected and stick together sometimes. So it's not just a tool to measure resource consumption you care about. It can be more. So it will be fun, definitely, like any new tool. There is this very known quote from Donald Knuth, and it's just the partial quote. So, perimeter optimization is the root of all evil. So why we should profile, why we should care about profiling. But the full quote is more interesting. So, yes, definitely, most of the time you accept that, and then you got a problem in production. So let's see what's the real full quote coming from Donald. We should forget about small efficiencies, say about 97% of the time. Perimeter optimization is the root of all evil. Yet, we should not pass up our opportunity in that critical 3%. What it means is a way different kind of statement if compared to the usual common quote about perimeter optimization is the root of all evil. It tells you more. It tells you that you shouldn't pass your chances to improve things in the critical path. But how do you know about the critical path? Could be with money, but we are talking about software. You should measure, you should look at it and compare with the part that get the money from your customer, okay? And now let's move into the flame graph representation. So we have talked about a bit about why profiling, why not, what kind of profilers, generally speaking. And now we will talk about a novel, is no longer novel because it's there from few years already, kind of visualization called flame graphs. Flame graphs are very useful when you have a system complex, pretty complex, and you want to quickly understand what are the parts in which you should look at, you should care the most. But in order to get used to that kind of visualization, we need at least to understand how to read it, and it won't be complex, believe me. So, in this case, for example, let's assume we have this very simple program. I haven't reported the main, but believe me, the entry point has the arrow, say, start here. So we have a method A that call a method B that is calling C and D, and is performing some heavy work. So it's not a comment, it's actual code that I deleted. So, but believe me, it's a heavy work. We have C that is performing heavy work, and we have D that is performing heavy work twice. So, click. So let's assume this is the CPU flame graph data collected of the previous program. Ah, right. How many people has ever seen a flame graph before? Ah, okay. So quite a few. It's very surprising for me, believe me, because most of the time is people that look at me and say, I don't know why I'm raising this hand, but it looks cool, so I will do it. So I'm very happy about it. So I will move decently rapid on this. So this CPU flame graph, the important bits. This is a stack trace. So if you read it, you should read it starting from the bottom to the top. In this case, I have collected this data per thread. So we do have the thread ID of who is calling the main method, is actually calling the stack trace in the form we have read it before. So we have A that is calling B. B is performing some EV work, and I'll tell you more about it. Then is called in C and D. The width of the rectangle are the amount of samples collected. So the more likely that specific method has been observed on the stack trace. So is more present, is more important for that specific kind of resource. Because as I told you, it's not just CPU kind of flame graph or CPU kind of sampling profilers. In this case, it is CPU. So the number of the sample are the amount of time you have been observed that specific stack on the CPU doing something. And very important, the x-axis is not the time. The people told me, why do I have a C here and D here? Maybe if I change the order here with the B that is calling D and C, maybe here I would get D and C. No, you won't, because it's just an alphabetic order. From the point of view of the colors here are used just to distinguish between frames that are near to them, because they maybe have a similar color. There is a color scheme to be understood, and we will look at it right after. But in this specific case, the greener doesn't mean anything. It's just green. Let's move to the next one. So this is a mixed mode kind of flame graph. To be honest, it is not super up-to-date nor accurate, because different kind of profilers that allows to create a kind of flame graph visualization data can use different color scheme. So I'm using the original one coming from Brendan Gregg, which has made it the very first time. He's one of the many that has worked on the flame graph visualization to the first time. If you search for Brendan Gregg, he was working at Netflix as a performance engineer before, and then he has started working to Intel. So the colors, very important. So the green is the Java kind of method. Then we have the aqua, that I chosen a very bad font here because it's barely readable, but the aqua are the Java inlined. How many people has ever heard about inlining? Oh, that's quite good. Okay. Then we are, for the ones that didn't know about it, I will speak very quickly later. So we have the orange that instead are pure kernel code. We have the red that are C libraries. In this case, it could be JNI or whatever. And we have the yellow one that could be the compiler, the GC threads, the part that is related to the just-in-time. So as I told you, this is just a color scheme. It doesn't mean that any profiler should report this kind of information, because every profiler got its engine that can use different methods to collect this information. And we will look quickly right after about the different types in that. And you got the thread ID sometimes, if you want it, is an option, as the base frame, the native ID. So let's move on. So inlining, what it is. This is coming from Cliff Click, that is one of the architects of the OpenJDK. Inlining is the optimization, but what it is actually inlining? So without looking, it's just to make me appear cool. It's not important, the figure. The inlining is the operation by using defined heuristic that could be flexible enough to happen dynamically or statically based on specific threshold, by which the JVM decide after a method has become hot enough if it is worthy, if it is eligible to be inlined. But inlined, what it means is that the actual call to the method doesn't happen. At the body of the method instead, with a few optimization coming from this, will be happening directly at the call site. And this is definitely the optimization. And why is that important? In general, is not that kind of talk that I'm going to explain why. But I can tell you that it's so much important to look at inlining that is worthy to be represented by a color, by profilers. But at the same time, given that it is a kind of an optimization, they make disappear, actually, the method call from the point of view of the observer that require more involvement by the JDK to communicate back what's going on. And I will tell you a bit more about it later. So in terms of the optimization, this is inlining. And the other thing that tends to surprise people, I won't get it longer here because I know already that there are people that know about it. Why native frame of a JVM? There are a lot of cases in which we observe native frame. We have talked early about C code, just in time, but even Java code. There are different kinds of intrinsic. Intrinsic are actually specific code path marked by the JDK in which the JDK can decide, or not actually, have candidate them to be replaced by the very different optimized version of that same methods that is no longer the Java one you have written. You did standard library of Java, actually, because you can't write intrinsic by your own. But the point is that there are many chances in which the just-in-time can replace the code that is no longer Java. It's something else. And most of the time, these are the so-called native frame for the flame graph visualization data. And given that they happen a lot, they are worthy to be represented by their own color because you would like immediately to acknowledge them, to detect them when you are looking at the profiling data. And there are different challenges, actually, about profiling. So let's move to the next one. The very first one is called save point. Save point, you don't have to read, actually, all that characters, but the important ones are the bold ones. So if you search for OpenJDK glossary of term, you will find about save points. When I start looking into this, many years ago, no one, apart from the JDK developers and the people that was caring about profiling, have an idea of what it means, save points. Now is a more well-known term. But even though most of the developer doesn't know about it, so if you have to explain it in a it's an anomaly, because save points actually are not defined in any spec of the just-in-time compiler. So a runtime of the JDK shouldn't have a thing called save point. It's an implementation detail, actually. But this implementation detail is what that allow different runtime to rely on a specific save state of your Java stack, your Java heap, or a specific thread and a specific part of the Java heap in order to perform specific changes. Some of these changes could be replace of a method that is being optimized, performing a de-optimization of these methods, or even collecting or marking GC roots, for example. So there are different parts of the JVM that would like or can rely on this specific save point. So a safe state in which perform these changes that are critical in order to make progress. And there are different types of save point operation. What I didn't tell you is that save point is a kind of, at least now, of a cooperative approach. So you issue an operation that requires your system to be in a save point that could be either local or global, but is not important for this presentation. The point is that you can perform an operation that require that state. And at the same time, the just-in-time, when it's translating your Java code into the actual interpreter or native frames of compile, whatever, it introduces a thing called save point poll. The save point poll is like an hole. And hole, or better, is a kind of unharmed time bomb. No, it's not even a time bomb. It's actually something which your code can fall in case there is an operation a safe point required operation that require your system to go into that safe state. And your Java program, your thread, Java thread, block. It won't move. And something that you don't write is injected by the just-in-time in order to ensure that there are happening these states in which they can change something. And the reason why I'm talking about about this is because of get all stack traces and get stack trace. They won't issue global safe point. I didn't told you global and local just for the people that knows already about it. But the idea is that these two information, as I told you, profiling data collect stack traces, sample of stack traces, in which a specific resource is used. But how you can collect stack traces? Very easily in the JDK. You can use these methods. You can use them through JVM TI, or you can use them directly from Java in some way. These require a system to be at the same point. That's why it's important to know that exists this safe point concept. And the other reason why I'm talking about that is that, for example, if you use a Visual VM, something that I don't really invite you to use, but if you really want to use Visual VM that is already shipped with the JDK, and I've been one of the many that in my past I use it, and you want to collect sampling kind of CPU information, and you enable through this xlog safe point thing in your JDK program that you would like to observe, you will notice that when you make it start, this is what you will see in your console. And it tells you the duration of the safe point, how much time has been required to make it happen, and how much time it takes to go out of it. Because as I told you, it could be global or local, but in each case, a specific thread won't move, won't make progress unless the safe point complete. So if you interact with the JDK, you await this to happen, and you block it until you're finished to do what you need, and then make it work and make it complete. You are introducing an observer effect. You are modifying your system because you observe it in a very intrusive way. So learning that when you rely on this mechanism, you are creating an observer effect, which effect could be important or not, something that could be decided. It's important to know the limits of your tool. And it's just one of the parts that are important about SafePoint. The second part is that they don't happen at every single instruction of your code. Why? Because if you make it like that, and you have a for loop that increments a single variable, and you perform a SafePoint poll, is another operation. So how much throughput you can get? Half than just executing the for loop, because you are performing an additional operation on the loop. So there are very specific points in your code where the SafePoint poll is added in order to not make it cost too much. And that means that you have a biased view of the world. You observe what happened in the JDK only when the SafePoint happen. It's very important. Sometimes there are things that you would like to observe as outside of it. Sometimes not. You would like to choose. Let's move it. So that's the taxonomy I promised about profilers. There are many types, so I won't list the single specific profilers. But it's important to understand that, yes, very, very important. This is coming from a slide of presentation on, I'm not outside of the, maybe. Okay, Johannes Beckberg, I'm not able to pronounce it, but you can read it. So actually, if you search for him on Twitter, he's a SAP engineer, is working in order to improve the specific code path of the JDK that is very welcome to be safer for most of the profiler out there. And he made this taxonomy in its profiling kind of slides. So you can have an external one, and there are synchronous one, like the one that will rely on this SafePoint mechanism to present you profiling data, like visual VM. Then coming from very ancient time for the people that have enough age on its shoulder, you will find the Forte analyzer that is relying on existing code path in the JDK that in theory is both undocumented, unstable, and unsafe to be used, but everyone use it to make very good profilers. And these are the so-called async kind of sampling, method of sampling. The actual name is async get call trace. Will change after the work of my friends because it's going to promote a change in the JDK to name it slightly differently. But that original code path exists from a long time and exists from so long time that Oracle itself used it, probably was Sun at that time, so it's 1991. And very importantly, given that they use it because it doesn't use the save point mechanism to coordinate with the JDK. So it means that it can observe the world, maybe in very broken states, even outside of save points. And it is a plus from the point of view of the observer effect, unless you make it crash the JDK, but that happens as well. And then right after, another kind of profiler that make a lot use of it is a sync profiler from Andrei Pangin, and there are few contributors, but things have changed recently about it. And it's a very good profiler for developers. I won't suggest to use it in production, but not because it's bad or good, because I don't use it. And you can have, and these are external, so they are using API provided by the JDK itself. While the built-in one, for example, are JFR or so-called Java JDK mission control that has been recently made open source, and they are relying internally on something very similar to this. So it's not a save point biased kind of profiling. So it doesn't make use of save point. They just emit these JFR events, sample events, about the stack with a specific algorithm, and it's already there in the JDK. You don't have to pay for it. Actually, you don't have to pay most of this for it unless you want to make it work in production, but it's a different story. So let's move on. So why I chosen a SIM profiler? I use it from a long time, and I know basically by heart the engine. And why is important? You should as well. If you want, yes, it's open source, so it's not that complex, actually. And knowing your tool allows you to know the limits of it when you use it, and when to believe to what is going to present. That is something that is going to happen in the presentation because it's running on Mac, so I won't trust at all to what I look. No, it's good, actually. So let's move to the next slide. So why effectively choosing it? Async get call trace. No save point bias, can collect corrupt Java frames because it's the nature of this async get call trace call. So I already told about that. The other one is that he's using another mechanism, could be not that safe actually, to collect perf events on Linux, something that I forgot to say, so probably we won't look at it with the Mac. But if you got Linux or any operating system that enable that, you can collect perf event. What it means? It means that it can show up even kernel threads, what they are doing. And as I told you, there are many parts of the JDK that can expose native threads. But if you write your own JNI code or you use a library like Netty that performs socket calls, or are you using sockets from the JDK in some way because of the JDBC, for example, you're going to interact with the kernel in order to send and receive those data. And when it happens, if you want this stack trace, this is using perf to match the Java side of the stack trace with the one provided by perf. And then you get the full stack trace of what's going on, okay? You have a very low observer effect measured. It works in the past with more than Java 6, now probably Java 8. And in the specific case of a SIM profiler is a kind of Swiss arm knife tool. So it's not meant to be the final product. It's more, or at least that's my point on this. As a developer, I love to use it because it's simple for me. It's a simple tool to be used. It's not a full fat tool. Sometimes there are people that prefer full fat, okay? And I can open a lot of issue to this poor guy. Now I open a lot of issue for a SIM profiler. It's open source, things has changed recently in few regards, but at the same time, you can interact with the community and they can prompt you, react, or respond. So it's a nice addition, and the code is there. So if you want to learn how that works, the code is there, so you can learn it. Let's move. Yeah, sometimes. Which one? Blame the wrong call. Oh, yes, I know that. That's why it won't fix. For good, there are a few ones, but it's good to know. So, because the developer behind the SIM profiler has worked in Sun when there was Brendan Gregg and other people. So he's even an OpenJDK, has been an OpenJDK developer. So the kind of interaction you got allows you to understand when he's not the profiler to be blamed sometimes. So, okay, perf under the hood, not so much under the hood. It's just general idea of perf. If you need to, I told you that collect perf data. We have a Macintosh. It's probably the first time I'm saying that. So we don't know. Probably we won't see them. But in case you have a Linux desktop, you will see them. How they work. Actually, you ask the operating system through a specific syscall called perf map open, probably, that I didn't report. No, perf event open, to map a ring buffer, so a queue, a bounded queue, in which specific events you are interested in will be raised by using the signaling mechanism of the Unix kernel. It sounds dangerous. And actually, it is, because let's move to the next slide. For this specific event that has been used by a SIM profiler, perf sample call chain, that's the stack, basically, the native stack collected, for given a specific interval for the actual CPU time of that specific CPU, it reports its stack trace if it's on the CPU, so the actual consumed CPU time. In order to get there, you should have the permit to do it. And that's why I'm saying that it's a very developer-friendly kind of profiler, because I can change my personal laptop system properties in order to enable that level of observability. Try to do it in production. They won't be happy, definitely. Okay, I'm not saying that you shouldn't do it. There are different AWS kind of machine that allows to do it at a certain degree. But at the same time, you should be aware that given that you are collecting information coming from the operating system, it requires a sort of trust. And the trust is a system property, actually. So that maybe you can't enable. And there are other problems that we won't dig right now, but it is important for you to be aware of. There is so-called skidding. Skidding, if you search for it, you won't find a lot of information in the internet. Actually, let's say that even profilers, perf profilers, will report you to blame a specific method or a specific part of a method, because with a SIM profiler or even with JFR, you can have the line of code of your method. There could be many layers of lying tools that doesn't make you report the actual, get blamed the actual real method. Okay, there are bugs, and that's not skidding. And it could be either that when the signal arrive, given that you got the process counter register in your CPU that switch the the next instruction to be executed, or to be honest, is already the next instruction to be executed, the one on x86. What you get is that when you observe it, you are too late. And you are blaming another method that has not to be blamed. And that's the so-called skidding. And it's because modern CPU are superscalar, are pipeline, they can perform a lot of speculation, and they have a full pipeline of instruction that they are executing. And they have the signal machinery that we have spoken about in order to collect the call stack trace. And this whole machinery and the speculation things can make to blame the wrong part of your code. And when it happens, you are done. I mean, if you trust fully the output of Profiler, you are definitely done. You shouldn't, and we won't during the workshop. And you should be aware of the differences between tools. So we are going to use for this workshop mostly CPU profiling, because the way by which I designed the experiment in which I designed the code make it suitable to be used. It's easy to be understood, the number of sample, whatever. But they are not only the only one. You can have a wall clock profiling, and the kind of challenges, the internal behavior of profiler while they're performing one or the other is very different. This one is coming from a SIM profiler, but you got something similar-ish for JFR, so Java Mission Control, within the JDK. So if you are performing wall clock profiling, what it means? It means that if you have a thread that is not doing anything, you would like to see it, because it's consuming for you the resources you care the more. That is time. It's not the CPU, it's the time. That's why it's wall clock. It's like someone is measuring what's going on for how long. So let's say that you usually have like 1,000 of idle threads, your JVM. Sometimes you got it. You get by default GC threads that are idle, unless you are doing something that allocated need to be cleaned up. You can have compilers. You can have a timer that happen sometimes. And it's going to be there. It will appear in wall clock. So it means that how many threads you can sample. There can be a lot. So if you are writing a profiler, you have to subsample. And you need to decide the strategy to pick up in a uniform way the most, all of them. Why is that important? Because in the workshop, we are going to make use of all the information, all the few relevant information coming from profilers. And one of them is the samples, because the samples tell you how many times a specific event has happened. But which event? What means 100? What are the maximum amount of sample that I expect for CPU profiling? This kind of core kind of question are very important to understand why you should spend your time on that specific line of code, okay? And we will talk about how much time. We are probably past 1 hour. No? Okay, I'm running. Okay, so, okay, and then the people will run away. No, sorry. Okay, so what kind of application I'm going to profile? So in my case, I work for the middleware performance team. I'm working with the Quarkus team. It's very likely the main product I'm working with. And I would like to present something that appears to be a real application stack. That doesn't mean that it's the best. It's the best for me. Love. No, I'm just joking again. So, but anyway, as I told you, we need to understand the dynamic of the system. So let's learn more. What's required about this system? You know, it's a shiny box kind of thing. So we have a Quarkus that, in our case, has an engine called REST-easy reactive, and it's performing most of the HTTP translation while interacting with the lower level kind of libraries. Which libraries? Vertex, that is a high-performance reactive frameworks, and we have Netty at the very core. Netty is a network library. It's very low level. It's not much more low level than JDK libraries that can perform networking, okay? And at worst, higher level, you got interpretation for the very basic things about HTTP. But for the most is network code, kind of code. And we needed to understand a bit the trading model, because when I will show you the profiling data, I'm rising the hype for the next part. Too much, lower your expectation. So we will observe the dynamic of the system while running, and we need to understand which part does things. You could replace it with Spring or whatever framework. My suggestion is that you shouldn't take it like a typical performance engineer. You shouldn't observe without caring. You are a developer. You should learn what you are observing and check if it matches your expectation. So these are the expectation. The expectation is that the native framework is a framework made of different event loop. Who knows about event loop? Yes, it's definitely a well-known kind of term. And these are called I/O threads. These I/O threads are meant to perform operation on the connection of different clients that connect to the server, to the application server. And they are using Netty, and they are using Vertex, and REST is reactive. And when you write some code high level on Quarkus, you can have two different trading models. You can directly perform things on the I/O event, I/O threads, so directly on the event loop, or differently, you can switch to a worker thread. So you have, let's call it context switch, but actually you ask a so-called blocking thread pool, please do these things for me. And when you have completed, report it back. So what is not show up here is that if you go in one direction, you should go back, okay? Because everything is then performed by I/O. If you have to perform a response back somehow, you should go here again. That means blocking and coming back, okay? Let's move to the next. And now we can start the workshop with the Mac. No. Okay. Okay, I can try.
The idea is to try now again.
Yes, let's try again. So. Let's try both.
Should we have a... Okay.
Ah, okay. Okay.
Is there any...
Exactly. So. I switch it off. I don't know how to. Perfect. We have two actually. Okay. Any question so far? There was very generic kind of introduction. Should be gentle in theory. Okay, good one. Ma è sempre USB-C? Ah, ma non è ancora arrivato. No, sta provando sempre la... In the meantime, for anyone that want to answer, is how many of you are using Profiler actively in their daily job life? I won't ask which one. It's not important for the, and we have a .doc one. So no, no, I'm joking. Okay. Let's see. The workshop itself allows to be run on Mac. Let me just tell you this thing in the meantime. So, as I told you, the engine of a SIM profiler is making use to perf to match what is observed by asynchronously asking the JDK to do things, to see what's going on, and the event, the perf event raised by the operating system. Still, macOS doesn't have the perf part. So how you can collect this information? They are using a different POSIX mechanism based on signals in which they register for a timer, and when the timer expires, they just collect those information. Okay, so it's a very different type of tool. You can very likely observe similar-ish thing, but having the full stack, it's nice. It's not always useful, to be honest. Sometimes if you see a socket write, you don't care what's going on in the kernel. You can trust it. But if you are curious, it's a nice thing. No? Yes, WSL 2. Incredibly, it works very well. I'm not saying incredibly because I wasn't expecting it. I tried the first time 3 months ago, and wow, it was just working out of the box as good as with the Linux machine. So, I can't, let me. Okay. Okay. Ah, okay, yeah. We can talk about it. We can try with mine. Yeah. With this one. Okay, thanks. There is a HDMI here. I can move it.
The cable was falling off.
Ah,
That's
okay,
why
that's why.
you didn't add the connection, so it will work fine right now.
Yeah. No, I'm saying yes before. That's never a good idea.
But it's already flicking, so it's...
See, if it flicks, it works.
No,
Okay, fine. Okay, so I can definitely sit down, put this here, or at the same time ask my friends to do it for me, and I can open up, I can stand up and do things. Okay, so we should connect first to the power. Oh, hey. Ah, right. 1 second. Okay. Perfect. So we do have this one, and we can use.
sto vedendo anche le
Sì, sì. No, I'm doing duplication. Display. Mirror. Definitely mirror for me. Okay.
Okay, yes.
With the USB cable, you also have the touchscreen
Okay.
Very good.
on your computer.
And
It's not needed to stay behind the computer.
no, we.
Can go there.
You can move where you want.
Okay,
You are
great.
totally free.
Nice.
I need to replace this.
So
The hatch, and it will be fine.
no, we need to connect the power. Yeah, we have to be sure that one shutdown. I can use it this way. It works.
Carica?
Yes. Okay. It works out of the box as far as I know. So let me try.
Kernel panic.
No, it doesn't work. No, it works. Yes. So I can make Sun to.
Yeah, but the moment it...
Oh.
Careful
Wait,
about
wait,
the
wait.
USB because it tried to
To send the display. Okay. So
Dammi un
what I
carica,
can
dammi
do
il
is
caricatore.
give,
Facciamo le cose semplici. Yeah, perfect.
Many thanks.
Thanks a lot.
Okay, 1 sec.
In realtà siamo in perfetto orario.
That's it. Se serve una presa diversa ditemelo che
boh, proviamo.
tipo questa.
Vabbè, Vabbè, ma l'asciutto dovrebbe andare, spero.
Okay, it works now? Yes, it works. Sanne, sei comodissimo, scomodissimo.
Faccio io?
Va bene.
Carica. Sì. Sicuro che vuoi il click? Tanto ormai sei al computer. Cazzo,
No, perché indico il codice, mi muove e faccio finta
devi fare qualcosa.
Ok. Finally. Alt P, giusto? E su greetings è il primo, quindi vai su. Prima gli dico che cosa ho fatto, che ho scaricato Hyperfoil e messo in uno script. Ok, glielo dico. Okay, so let me very briefly describe what this project is. So, the project is a kind of is using the archetype defined on the Quarkus site to create Hello World application. So the one that allows to have the native compilation in and has already a skeletal of the dependencies you are interested in for the project. So from this point of view, it's simple, but it's complex enough that you can observe the full stack. And I made a very simple Unix script in the folder scripts, by which you can run it. You can even call it with -h. So let's call it with -h, with the script with exactly -h. Because you have the UK mapping. I have the Italian one. Sorry. Okay. And you have different type of arguments, even way more than the one that we are going to use for the workshop. So you can customize the kind of events you are interested in. You can change the rate by which running your test. You can configure the number of client connection, the number of thread of the server, and the output type in which you can observe your system, because a scene profiler allows to collect data directly in HTML format that shown up as flame graph. We will look at it right after the first run. Or you can collect JFR kind of traces. JFR kind of traces are more rich. They are richer, they have more information, they can collect the level of compilation of specific methods. You can have a line of code if they works, unless skidding and other interesting problem. And most importantly, what I told you before about inlining, because I wasn't lying, no? Inlining is important. It's a cooperation. So you have to tell the JDK, please show me the right thing while I'm profiling, even if the methods are being inlined. How you should do that? Let's go to the script itself, SH. So it's benchmark SH there. In just the file, yes, the executable file, benchmark SH. To click, yeah. If you search for debug non-save points, or you can search for save points, is the same. Okay, this is the parameter that I have added to the Quarkus application in order to not forget to report meaningful debug information for things that are being inlined. Not just inlined, but definitely inlining things lose most of the information because they lose their save points. The exit method save points, one of them. And because of them, maybe you don't know that you are in inline method. And you will just observe the base method. So for fun, you can remove this and make your script to run. And I will show you now how to make it run. And in that case, you will see how the flame graph change. So what I'm giving you with this workshop is a playground that everything already there. you got methods. These methods do things with the stacks. You got the load generator. So we have chosen Hyperfoil because it is an HTTP load generator that we have made in my team, the team I work for. And it's performing the right warm-up in order to be sure that the application server is warmed up enough to collect good information out of it. Even if all the people will tell you, you don't have to run profiling and benchmark on your desktop, unless you know very well how to do that. And even though you should be aware that what you are observing could be very different from what you will observe in production. But the tool, the mechanism are the same. So it is important for that kind of learning process. So let's run it with the greetings one. That is the yellow word. I will show you later the code. Let's make it run. So very first, right, you should build it. Maybe we change something in the source code, but at the same time, you should first compile it. Okay, with the -u, you can define the endpoint you would like to stress on your load generation. In this case, I decided that the base URL is the hello word, the greetings. So in this case, we don't need to provide the -u. By default, he has configured the clients to have 2 threads because the Hyperfoil is an event loop-based load generator. So he's going to use a 2 thread just for that. The application, Quarkus, has been configured to use 2 I/O threads, 2 event loop. And at the same time, the number of connection of the client are 10, okay? And it's going to perform an all-out kind of throughput because all the tests are being designed to provide the bugs that, when fixed, produce a lot different peak throughput performance. So we don't need to care about systematic problem by performing load generation in the right way. Okay. So let's make it run. In case you are doing on your computer, it's very important that you have to download Hyperfoil and place it with the named Hyperfoil in the same folder of scripts. So you got scripts, you get Hyperfoil. Because by default, while running the scripts from the scripts folder, it's going to pick the Hyperfoil installation directly local there in that specific path. What's important? So on the Mac is going to use something with PS, okay? Why this is showing the PIDstat output? So the other requirement, you got to install systools on Linux that should have a PIDstat, okay? This is collecting during the execution of the test. Let's go up a bit. Okay, this is collecting during the execution of the test the user, system, guess, wait time on I/O, and the global CPU usage. Okay, the machine I'm using is a 12 core with 6 physical core. I told you that the Quarkus application was using 2 I/O threads. So what is the max percentage that we expect from the server application while it's fully maxing out 2 cores? Is 200. This is more. So there is something more going on, okay? Now let's look together at the flame graph and try to understand what's wrong. And please look at the numbers as well. So is 96 message per second, okay? Okay. So, as I told you, let me refresh your mind. The red one here, are the J and I call, The orange one are the kernel. The green one are Java code. The blue one, poorly, a SIM profiler cannot detect inlining in the middle. So you will just observe inlining when it's happening on the top. But in this case, you got the aqua one that represent inlining methods. And you have the thread ID here. So when I told you about the architecture, I told you that if everything is running on the I/O thread, the event loop, we would expect everything to run here. So these are vertex event loop threads. And we got 2 of them, as I told you, was 2 I/O threads. But what are this one? It's another thing. I told you about another way to issue call. And the other one is by using a thread context switch. So you have another event executor, another executor in which you can ask to perform your operation and come back. So if I perform the search for the keyword hello, so Control F, hello, nothing, no, exists, it's very tiny. Try to click here. Just click in this bit. Okay, it's super tiny. No, it's not even here. It's here. It's a super tiny thing. Somewhere is one of the few threads. Or no, there is nothing. Probably you haven't searched right. Try again, because matched is 0%. Because in the right bottom, you will see the Control F. It's the Control F not of Chrome, the one of Firefox. Is not, yes, because when you perform Control F on the browser, is not going to use the engine to search a specific frame within the flame graph of the HTML thing. Okay, hello, go down. No, it's 0%. I can trust it, or kind of trust it. The idea is, in this specific case, it wasn't by far the most important operation to be performed. And hello was the domain method in which I was just returning a string. Very simple. The fact that we can't find a single sample of it is not weird, effectively. I try hard to search about it because I was expecting at least one sample. But the reality is that this method is not doing anything interesting. We will look at the method later. But the most important information to collect here, and I will do the math together quickly now, is to understand what's the dynamic of the system. So let's do something different that I'm not usually doing. If you perform Control F netty, for example, you will see what are the parts related to netty, which are responsible of the overall CPU usage, because as I told you, it's not a wall clock, it's a CPU kind of profiling, this one. So in this case, the 98% of the cost of the method direct and transitively, because of the other call stack, belong to netty. So it's mostly netty thing, okay? And what's important that we should understand is the meaning of samples, if they match our expectation. We know already they won't match, because we were expecting from PIDStat 200%, and this is more. Why is more? Let's look first if the one that we expect are fine. A single event loop. There are some missing information that I will provide you now, but you can check on the async profiler guide, and you can check the same on other profilers, actually. For CPU sampling, it performs sampling at 100 Hertz. So it means that in 1 second, if a single core is burning completely the CPU doing thing, it's going to collect 100 samples. given that it's output by the script, we are collecting profiling information for 20 seconds, okay? Let's count together the number of samples of this event loop. So if you go with the mouse on it, you will see that is 2K. Is expected? Yes, because are 20 seconds, so in 10 seconds, you would have 1K samples. In 20 seconds, we have 2K samples. So we know that this thread is consuming a full 1 core. And we got 2 of them. So the event loop, the I/O threads, are both performing 100% of 2 cores. And that means that the additional one are this one. And these one are smaller, the base. So the number of samples is less. But how much is less? If you go through them, it's 260 samples. That is 1/10 of a single core for 20 seconds, because so it's 10%, actually. And someone is more, someone is less. So the additional, unexpected CPU time is being burned there. So the very first problem of this benchmark is not what it's doing, but how it's been configured. Because as I told you, we were expecting instead to have just I/O threads. So let's look together at the code, and I can show you how to fix it or properly configure it in order to match our expectation. And then we later check again how the event loop change and how the numbers change. So we needed to add an annotation on these methods called non-blocking from small array. I wasn't expecting you to fix this, okay? But it's an important information about why you should learn about the dynamic of your system, why you can't ignore it. Because in this case, if you ignore it, you're going to fix the wrong thing. You will look at the flame graph and say, okay, the problem is there. You spend your time in something that is not worthy, is not already matching your expectation. It's like a physics experiment, right? So we set expectation. So we have added the non-blocking, a very small parenthesis on this. By default, Quarkus try hard to help user. It's not a pitch, but you can ignore him too. So the return type of a resource method, that is the one that should be issued, the respond back to the HTTP call, is using the type to detect if you should run on the I/O thread or not. So if you are using asynchronous type, like completable future, completion stage, the reactive kind of types, you have by default running on the I/O thread. But if you do anything other, no. Is going to use the blocking thread pool, as I told you before. And string maybe has been obtained by issuing a call to a database. So I can't run it on the event loop, because event loop should never stop. No. So we have an annotation to instruct Quarkus to ignore the original ergonomics and then just use the I/O threads. Let's see if things now match our expectation. We should compile it again because it is an additional annotation. It won't happen that much during the presentation that we are going to change things, but sometime will happen. And if we run our experiment again, always on hello, it's waiting 60 seconds of warm-up before profiling for 20 seconds. So as I told you, the script already try hard to make things to be warmed up in the right way. And I can report you a change in PIDstat now that I haven't fixed yet. No, I'm not a kernel developer, so I'm not expecting to fix it myself. Or I should read better the new doc of a PIDstat. In the previous PIDstat implementation that should report this CPU time, it was reporting 200 on my machine. I recently made the mistakes of jump twice to Fedora distro, and PitStat has slightly changed. Probably is related to the way by which you perform averages or sampling of the CPU time. So in theory, that should be 200, okay? The source of truth will still be the samples collected by a SIM profiler, because regardless what this tool can do, it's directly asking the operating system to emit perf events for actual consumed CPU time. So it's very reliable if the signaling things works. And now look at the profiling data, how much has changed. And it's changed a lot, because we have now see completely disappeared the additional threads on the left. That was that very small, tiny parts. We have this giant event loop like. It's very small, but if you increase it, is the vertex event loop, is one and the other one. They do basically the same thing, and we can try to call to search for hello. Maybe now we are lucky. Never again. No, I can see it. It's there. Maybe. Oh, no, no, it's not. No, go on the top. I can see it. Or maybe not, again. No, no, we are not lucky. It's not surprising, actually, because effectively it's just returning a string. So. But at the same time, what we are looking at now is the dynamic of the system when it's fully reactive. So when, or is fully asynchronous. If you are going to use just netty or vertex, or STZ reactive through small rai, whatever, or a web flux, if you are using Spring, you should see something like that. If you see something different, you should understand where the CPU time is spent, okay? So the actual bug, there is no bug in an hello world, unless I'm going to send PR to the Quarkus team. It's just to understand we made some assumption, we have validated they were wrong by the actual configuration. It happens all the time, okay? The other thing I would like you to look at is why I was so interested into the kernel frames. You shouldn't learn Linux, POSIX programming. If you do it, it's not a bad idea. Because, for example, given that netty is the network framework, if the system is so fully loaded, the very first question that I would do, for example, is, I'm delivering the best throughput that my machine can perform. It's a very complex question, because you have many things. You have the frequency, the speed of the caches, the speed of the memory, the speed of the network. You have a lot of information, okay? But there is something very simple related to the dynamic of the system that gives you already this information, a part of it. There is a call in the kernel stack trace called epol_wait that when the netty system, the network layer, doesn't have anything to do, will just sit. And that's to answer not the question if the server has been effective, but we are really pushing the hardest we can, the server. Because if it's going to wait, because it doesn't have enough to do, probably we are not pushing hard enough. Even if it says that it consumes the full CPU, it doesn't matter. If it spends the time on waiting, it means that wasn't enough. Let's see if it exists. And it exists. So at a certain point, when it doesn't have anything to do, it just calls a poll wait. It doesn't happen a lot. And what's surprising, or I would be surprised by it, it consumes CPU. This is a CPU flame graph level of profiling. It's not wall clock. It's not the time spent by waiting. It's a different thing. It means that even waiting costs, because you have to interact with the kernel. And that's why you would like to know that kind of information, okay? So we know that wasn't enough. Enough, probably it means that if we change the connection, the number of connection, we can have enough parallelism, concurrency in the system. What I know that I didn't tell you, but I'm saying that one now, is that the native framework, through the Vertex configuration, decide to distribute the client connection in round robin between the two threads. So you have 5 connection here and 5 connection there. And I'm not using pipelining in C++, in HTTP. So it means that for each request, the client should await the previous response in order to send another request. It can't just fire request one after the other. So it means that how many concurrent requests can you observe in your system? At best, 10. The number of client connection, because each single client connection can't issue more than one concurrent call. So probably that's the only way to increase the throughput of your system, is to raise the number of connection, okay? Let's close it. It was just the hello word, you know, so there is a lot about this thing. And before moving, any question? Surprising results, unsurprising results. Okay. So let's move. We can delete the previous flame graph. Thanks. So they are collected based on the date, time, blah, blah, blah. So you won't forget. And we can move to the logging one. So the logging, let's look to the, let's look first to the resource, okay? The entry point is a person /age/age. As you can see, we have non-blocking. In theory, we could have used a synchronous construct, but in this case, we have built a fabulous, super fast in-memory database, so we know that we are so fast, we shouldn't care about I/O. And in that case, it means we do not care about blocking the event loop because we never block. It's a fully concurrent thing. And in this case, this fabulous database, we can't do much more than asking him to stream the data. The data are a database of person. And it's performing a query to filter those person. It's using the stream API. Why is using the stream API? Is a legacy code or is not legacy code, whatever, exists. This code it is what it is. What it does, it's using a construct called pick that during the iteration along the stream, it won't modify the stream and it allows to report through finest, if you have configured your logger through finest, information about the person that has been collected. Then we have an actual filtering in order to have a specific person that have that specific age, and we collect them through a list. Very simple. And later on, given that we still would like to collect which are the one filtered, we have added a for each to log those information as well. But is finest log. Okay. Let's see what happens if we call our scripts with the -u persons /age/42. Okay, without the slash. Exactly. 42 is not about movies or it's my age. Because there are a kind of movie that talk about specific numbers. So in this case, it's not magic, it's my age. Was my age, has been my age. So we run it. Let's see. The throughput of before, I didn't report it you, was about 50% more than while using blocking threads. And was using one core less. So that's why it's important to understand the dynamic. You won't get just better throughput, but better usage of your resource. No? So even if we know that this information was lying, we know we can't have more than 200%. So even if PIDStat is reporting slightly less, that what's the real one. And if any of you is running this same example and got to 2000, I'm happy for him. He's going to tell me how has obtained it. But okay, has worked. We have 24 messages per second. The number of person are very tiny. And we are using JSON as a format. So the fact that you got a lower throughput doesn't mean that your application sucks. You should have your expected level of performance that are matching the kind of resources, hardware and software you got. But we have a baseline with a specific number of bytes for each message that was the hello word. That's the best we can do. Unless the person is much smaller and is single one, we always get lower performance. We can't get anything better. And that's why I provide you the hello word example, because it helps us to counter-validate if what we are observing is not just right, but is good enough considering what kind of work we are doing. Okay, so I can tell now it's a better result. Let's look at the flame graph. Ah, yes. Anyone is curious, would like to guess what could be the problem, please? The logger. He's always the logger. No, he's not. Maybe. Not just the logger. I tend to blame stream as well, but this time, no. Could be. It's a good point. And believe me, this one, I shouldn't say that. It's collected from a real world thing. It's not exactly like that, but was very similar. Yes, definitely. So by default, is not collecting finest information, if you're curious about it. And yes, let's see together what it is. And as I told you, it's sadly a real world kind of experience. So we still have 2 event loop. Let's check the global number of samples first. 2K, it's fine, is what we expect. The best we can get from 2 cores, like application. Equal weight, Control F, equal weight, just to know if we are pushing hard enough. Way less than before. So it means that whatever the application is doing is making him busy enough that it never sleeps. Probably is slowing down clients, because we knew already that 10 clients can push hard, like having 100K messages per second. Kind of match, a gross estimation. Now, let's move to the top. Yes. And don't need to zoom, really. I mean, okay. Yes, it's related to logging. But it's not just logging. I would like first to observe a couple of things that makes profiling very complex with the reactive application, with the stream application. When you create a reactive pipeline, when you create a stream, you are not doing anything. You are just interacting with the builder to create a processing of what is going to happen later. And that means that if you have a very readable DSL, you won't ever translate in a very readable stack. The opposite, actually, most of the time. And most of the time because this kind of DSL make use of lambdas, which name are not easy to be read. You can barely understand where they are coming from. No? So in this case, for example, we know that there is a list by age method on the very top. The actual very top is here. This Quarkus REST invoker list by age and very long UID, it's the magic of Quarkus. I didn't told you before. There is no reflection. Nothing. So Quarkus create a class file, and this class file is strong type, whatever, the best you can get. exactly what you are going to write yourself in order to perform that operation. And that's what's doing. And you can see it in the flame graph. Indeed, the cost inherent of that specific method is 0. Because effectively, it's going just to call another method. That is your code on top of it. Remember, these are called stack trace. So, for example, the cost within a specific method is the one on the top. Oh, I could use this. Okay, is here. This is the cost of whatever it is, this lambda. The inherent cost, the Java code within it. And is always like that on the top. But the one created by Quarkus doesn't have anything on top of it that is exposed directly to the very top. So from the point of view of this specific case, it doesn't cost. Let's look here if it matches our expectation. So it's filtering by age. As I told you, is not very readable, as good as the stream itself. It's performing few things, including here now. Oh, a lot. It's so much that appear here and here. And you got a formatter coming from the login service finest. So yes, there is a problem with the logger. It's not the configuration, actually. But we will look together what it is. But this is calling a formatter. This is log back. A few years ago has happened. It was a bug, actually. So that's why I'm reporting it. And we can look at the login service first. So let's look finest. This is one API. It's bad because it's creating maybe one array, Alt P. Alt P. The presentation mode. Yes. Okay. So the login service is something that we have no control. So I didn't tell you, but this could be any bridge proxy logging framework you are going to use. Okay. These have a very minimal API, but the problem is that it could be broken. And when it's broken, what you can do? You can't you can fix it. I love open source. You can send a PR. Maybe the PR is going to be merged. 3-4 weeks later, your customer got a problem now. So you need to fix it now. In this case, the problem is that, gosh, they format the string here before checking the level. It was a real nasty bug. A lot of people got it. And the format thing was actually pretty costly, not as good as much as the ER collecting in total, but we will look at it later as well. But we have is finest method. So we can make use of is finest method to make so much more uglier our beautiful stream, but without that bug. So we can fix it. And let's start with this. I can use isTrace to destroy the beautiful stream thing that I made. It's not important. We know that this is going to solve it. We would like to have a proof of concept that set the new expectation level in case we are going to avoid the finest call. So for this specific experiment, that's not a fix. We can just remove the peak, and we just remove the for each. You can rewrite it at home, make is finest, whatever you want. It's going to be obviously slightly different, but that's the best you can do. The best you can do is just not make it happen. And sometimes it's a solution, sometimes it's not, depends. And the other one, I told you about here now. There was here now with some red thing on top of it, no? If you search for this, get the nano time adjustment is a JNI call. And if you search on Wikipedia on VDSO, VDSO is a shared region between the kernel and the user space in which when you would like, if you have a trusty clock source time, and you would like to collect the actual time, you just without any syscall interact with this shared region. And it shouldn't cost that much. But if it's in the busy loop, and it happens a lot, and maybe you are on AWS, and you have no enabled trustful clock source things, then it's going to cost a lot. It will issue a syscall. I didn't go so far for this presentation, but the point is that if it's there, there is a reason, okay? And definitely, we really needed to ask the year in a busy loop. I mean, it changed one time a year, so maybe it's not such a great idea. So let's go back to the application and perform another change. I could run 2 times again, but it will be too long. So let's speed it up by removing, let's see where it is first. Let's go to age. Person was a record. And in order to make the code very simple, they just performed year now get value, that is an integer value that represents the year, minus birth year. So in this way, they have one stable information that is birth year, and they can dynamically make age to appear every time by issuing year. Given that we are setting the highest possible expectation of what means to fix this thing, I'm going to create a static final variable that contains the current year. In the real world, you should find different way to fix it. But given that the problem is that we are continuously asking what's the age by using the year again and again and again, probably is not a good idea. You can change the algorithm, you can find your own way to fix it, actually, really. It's not, we are not focusing here on the solution, but on the problem. And the problem is that these appear to be very costly for our application. And remember, the original performance of this thing was about 26K messages per second, something like that. Now let's compile it again, now that we have fixed both the logging, supposedly, let's see, and the age, and see what we can get out of that same 2 cores now. My broken PID stat was reporting 187, 86 kind of percentage. That was nearly 200. So I was expecting something like that. Even if it's broken, should be reliable while broken at the same time. No, it's not. Okay. But now we will look at the samples collected and we will see what's going on. And if that's worked. Because this is linking to the question made by the lady there. So maybe the stream. I tend to blame the stream as well. But before my own expectation, let's look at the number and see if could be the stream by the end, when we have fixed the actual bugs. Because when you have something as terrible as I shown you, these are bugs, and not performance improvement. Okay. We have now goes from 20-something to 78. It's quite a hell of improvement. It's like 3 times in a row. Let's see at the frame graph if they are decent or not. Okay, and now we can check for Control F age to see, I don't remember the name, persons, go up to the very top, super very top. No, probably is this here. The invoker handler is the one on rest easy. Try to invoker handler with the case sensitive, so uppercase is a case sensitive, so invoker handler with the H, yeah. Okay, no. I don't remember the name. Let's check the name of the repository of the service, or login service, whatever. No, now we have removed it. So let's check just the name. Okay, exactly, that one. So we have the full call stack of it. Okay, it's in total, it should be a very tiny percentage of the whole CPU time, okay? Let's click on this and see what's happened inside. It's very similar. So we have a pipeline. This pipeline is just collecting some information. They are using for each remaining that is using something to add to an array list. And then we have an age person repository, blah, 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 lambda, something.test. That is the predicate, okay? And it's mostly inlined. So I can tell you that for this specific application, you can try at home. You won't get much better performance by using a for loop in which you are going to do that one by hand, really. It's very unlikely, because if we trust our concept of what are the resources we care, if this is a 100% kind of using application in terms of CPU time, the most important resource here, according to the flame graph, are the CPU time. For the CPU time, this is going to be like 2% of the whole CPU time usage. I know that's the part we are in control of. But at the same time, it means that unless we do something terribly wrong, we can't get more than 2% more performance out of it in terms of CPU usage. Is it true that CPUs are pipeline? They have a lot of characteristics that doesn't make performance to be composable. You can make just some of the components. But at the same time, you can get way more. So in this case, you won't increase 50% because you are removing a bottleneck of the 2% while you are using the most of your CPU time, okay? And it's the profiler that tells you this information. And at the same time, the other thing is that I dislike Stream because they force me to allocate a lot. I don't like it, actually. No, it's personal. I don't like allocation. But at the same time, I told you that profilers, like a SIM profiler and few others, report the amount of CPU usage performed by GC. So let's search for GC with the G and C, or G1, if you want, with G uppercase. It's the yellow one. So there are good reasons why you can see it, because it's probably super tiny. And I told you that this one collects information in a safe point, unbiased way. So if there is something going on outside of the safe point, like, for example, pauseless garbage collector can perform a marking of Java references between the safe points. They don't need to stop your application. They do things and can do it concurrently with your code. So it means that a profiler that is safe point unbiased will show up that cost. And we are in the very hot top method creating a lambda with the things, so the whole pipeline. I would expect to allocate a lot. Maybe it is, but it's not important for the performance of this case. That's the core thing. So that's the part I'm never too smart to look at the profiler, because even my own bias is broken for this case. It's not right. It's not the GC the problem. It's not the stream to be blamed. Okay, let's move to the next case. If you have any question, like I should ever use a stream, the answer is no. No, you have to use it if you really have. Okay, the other example is the time one. And I don't have to spoil the thing by thanks. Okay, Alt-P. Okay, this kind of things is slightly different. So We are already, we remember the annotation thing. So it doesn't have non-blocking. At the same time, it's using tick. Tick is not an asynchronous type, not at all. So our expectation, given that we don't have the non-blocking thing, is that this is going to be issued on the executor service, the blocking one. Is not going to be executed on the event loop. That's our expectation by looking at this code. There are good reasons for that. I can tell you, yes, there are. Because this one is going to emulate an external service, the time service, or UTC time service. You can think about it like an external service that give me the tick, the actual time now. And they have an SLA. I can change it. It's a client library. And this client library is using some service, cloud service, that is rate limited. Or worse, is client concurrency limited. You can't have too much client performing that call or calling that operation. And each time you have that call is a 10 milliseconds like latency. And that's why I can't use it on the event loop. Because if you perform such a blocking operation on the event loop, you're going to slow down everyone that maybe has been enqueued. So that's, in this case, we cannot detect a misuse of the framework. The framework is using an external blocking system. So it's right that we expect to see event executor service blocking. Now, let's run it. You can replace the external system by database, actually, with an actual repository. It is that kind of problem. Here we got already where the problem is. And then you got another hint if you wait by the end of the execution. This looks like a obvious problem, but you can believe me that I talked with, I can't give the name because it's not nice, but I can talk with some lead performance engineer coming from other companies because we are great. We never do things like that. And it happens all the time. It happens to me as well, a lot of time. You can't challenge everything. Sometimes you have bias. You follow the bias and you go straight. But the reality is that you should observe the word first. No. In this case, there is a great observation here. It's a very low request per second. So anyone that was going to raise the hand probably was looking at the CPU usage. That sucks. You know, there isn't even I/O. It's a bad word. I can use it. I can use it. I can use it. Okay. And what happened in these cases that I observe many times is that the people look at the CPU flame graph. You shouldn't, but why not? It's a workshop. Like, look at it and see if it matches our new level of expectation out of it. So, and in the meantime, is going to open it. What are your expectations about this flame graph? What's going to show? The most relevant part. It will be surprising, believe me. You will see. Maybe. No. Okay, just close it and open a new one. IDEA got a very short history for the memory of the... And we can remove the old one. It was nearly 51, probably, 49. 49. Yeah. Maybe it is. Okay. Okay. So, how many times you have observed things like that? 0? now you know because now you all understand the why of the reason why Quarkus choose native compilation. Let me show you why. First, count the number of samples. Let's go on the bottom. 255 was 4K to full core, and a single full core is 2K, right? So we have a 10% overall CPU usage shared among all threads. But at the same time, the number of requests was fairly low. But what happened to the just-in-time when you have such a fairly low number of requests per second? It doesn't know yet the ergonomics, the dynamics of your system. It's learning. And when it's learning, it's performing a tired compilation across the very different components of your program. And these components have their own threshold. The JDK got their own threshold to decide for each one of these components when it's time to compile it to the higher level and quality of compilation, or the mid-level, or just collect meaningful information out of it in between these two levels that are the so-called C1 and C2 compiling level. Things like intrinsics, so a very optimized version of your method, happen at C2 level, for example. So it means that if you are a C1, nothing interesting could happen. But still, you are responding to external client system. So if you search for C2, so Control F C2, that's what you get. Ta-da! So the most, let's say, nearly half of your samples, that is still 5% of your CPU, is spent while compiling things that maybe will be hot someday, one day, okay? How much could be relevant for you? 0. So if you are going to use the wrong compiler and you are not cross-validating with other type of events, like just looking at the request per seconds, actually, but if you ignore the request per seconds because you don't have that one, you just have tracing data coming from customer, check the number of sample, ask the number of cores, ask for the duration of the test, search for C2. And if a lot of CPU time, if compared to the global one is spent there, probably doesn't mean that much what you're doing. No, actually. And given that the fairly low number of requests per second is not surprising. But at the same time, it's very useful to look at dynamics of things. What happened is still parsing thing. And, you know, at startup, you got this one all the time. And it's sharing definitely that same amount of CPU time with your application. That's why the beauty, for example, of native compilation. You won't pay for that one, actually. And if you spend most of your time doing startup stop, probably it matters because you want to reach the peak throughput anyway. And when you reach it, you are going to die. So why paying for that? I'm pitching native as well. Okay, so let's check another way to look at this same data that could be more useful for our purpose. Because, you know, it's a single resource, single endpoint kind of application. Now we make a pause in a very few seconds. And when you got something like that, it's easy to spot what's the guilty part, you know. You don't have much complexities. But in the real world, you would like a kind of a profiling that match better when the most important resource is time, because it's not the CPU here, as you can see, but the time, where my time is spent. I would like to know. So minus U time minus E wall. No, E exactly wall. Okay, this is using the wall clock profiling provided by a sync profiler. It doesn't work that much differently from the one of other profilers. I will try to, again, to explain you about the sampling thing, and I will tell you why I don't like Visual WEM. I already told bad stuff about it. Java Mission Control, for example. I told you that there are internal built-in kind of profilers within the JDK. One is the one of JFR. JFR collects sample in a way that is surprising to me. So when I try to count the number of samples, that doesn't tell anything meaningful to me in absolute time. They tell only meaningful things in a relative way. A against B versus B. They have different number of samples, so the more, it's more important. The less, it's less. But I don't have an absolute measure. So I should use other metrics to make sense of it. While, for example, for this one, is slightly simpler for me as a single tool. Not that simple, actually, because as I told you, it's a whole clock profiling. So it means the most important resource is time. So what happens if your many core machine have an ergonomics that makes to create a lot of parallel GC threads that doesn't do anything? They are just sitting, awaiting you to allocate. They would appear, yes, where is, yes, they will appear. Because they are spending time. They are not doing anything meaningful. It's your problem. As a profiler, I told you, they are spending time doing nothing. So, for example, we have G1. So if you click on G1, you can see in which call it is by waiting its work, because it is what it is. And indeed, there is a waiting on Futex, but it's waiting, actually. And then we have the reference queue, for example. So we have the weak reference machinery, in which you create weak reference, there is a queue, it's been queued, it's work for the GC. And you got them one as well, here. So you can observe every single thread, including compiler threads, and knowing how many of them are waiting to do work for you. That's nice. So even if it's disturbing that you got so many threads, you can filter out, actually. But in this case, I would like to show you the global work. So we know that is an executor, right? The blocking executor. So if we search for executor or for time, I would expect to find in some of these stacks. And then we can look at the number of samples. Click on one of them. Executor thread 10 is not the event loop. This is the blocking thread. Now, let's look together at the number of samples again, because I would like to help you to understand how to make sense of this. So we have said that is 100%, 100 hertz the frequency for the CPU profiling. And the more core, the more they are. But for a single core full timeout is that one, maxed out. For the time is different, because it's different the method by which things are collected and sampled. So is 10 milliseconds by default. No, it's 10 hertz, actually. And that means that every single thread that has been selected among 8 times at time will have a different tick of what's going on. It's very complex. In short, you can expect about 10 hertz. The reality is that a SIM profiler recently make more adapting the frequency, because if you have a lot of idle threads, maybe you would like to increase the frequency in order to be able to collect of more of them information. Because similarly to JFR, it's subsample. So you have maybe 1,000 of threads, but it pick just 8 for each round of the tick. So in order to be sure to take more, it increases slightly the frequency. And in this case, he decided that so the frequency shared among all threads, make it appear 400 a time. So given that the test is 20 seconds, if we collected 10 samples for 1 second, we would expect 200, but we have 400 for each thread. So given the number of threads is so high, it collects more samples. So very simple. No, it's not simple, but at least to give you the idea. Now, what's our service is doing? It's calling time service, and if we go in time service, we can see that there is some synchronizer to limit the concurrency. And it's just sleeping. Obviously, you shouldn't see something like that, because if it was an actual real client library talking with an external AWS server, you probably have a wait for the on the output stream or the input stream while waiting the response back from AWS. Okay, but the problem still old. No, what we can do to fix it? No, any idea? Then we can make a pause and we'll create hype for the next the fix. Anyone want to try it out? How to fix this? Consider that you have a limit. So the best that the external system can achieve can't go over this. So that's the maximum you can get from the external system. So when you have a database, you have an information that have a certain expiring time. For example, if I told you that the time service got a 1 second granularity, for example, it makes sense to try hard in 1 second to call it 1K times. Probably not. It's not going to change. You have rate limiting, and the number won't change in less than 1 second. So what you will do with the database, you can cache it. Exactly. So the solution is caching in this case. And we can observe the system, how it behaves with the form of caching. But now let's take a pause. We have the time for the pause. No, it's not nearly done. Yeah, you wish. I can show the caching thing. Unless you want first to see the solution, and we can take right after the pause. It's up to you, decide. I can go on? Okay. So now let's look at the time cached endpoint and Alt-P to make it cache the time resource and Alt-P. So beside how it is implemented, the kind of trade-off are very real in your system. So when you have a resource that is definitely limited, and you still would like to provide the reactiveness to the other system that still requires some information to move on, there is some form of caching that should be in place, okay? And the beauty of caching is that it enables saving resources, as we expect, and you know, modifying the system like that doesn't appear to be like a performance job, because it's not. Profiling is not a thing for performance engineer alone. What I show you now is a developer tools in which you observe your system, you observe your dynamic, you observe what resources are important for you, and you define other strategies to make use of that same resource. You set up an experiment, you still need it, and you just move on. And in all this process, there is no role. You are just a developer, actually. No? So, beside what it's doing, let's see the key part. The key part is that we are scheduling every second a request for the external service. Very simple. So, every second is going to update a local cached version of that same information. And this information is making use of an asynchronous type. So I don't need to configure non-blocking on the endpoint, but Quarkus automatically is going to run this on the event loop thread. So basically, each second, you get a new, fresh, updated information. To be honest, it will be very likely stale when it's going to arrive to the client. It's not, as I told you, it's more the process, the dynamic that you should care about. So the caching is going to enable two different feature in your application that we would like to observe and see if it match our expectation, even in terms of performance. But it's very unlikely that we can get less than 400 requests per second. It was very bad. Even if I bring it by hand, packets, I will be faster. So in this case, event loop running, and what else? Still the same information, so we are still making use of tick, so we are not sending more data. It's not actually right. When you use cached data, you would like an expire time in order to tell the client that is maybe not valid anymore, but say that, let's run it. So minus U, cached, minus E is not required anymore because we would like to check the CPU profiling if it's as bad as it was. And still remember the results coming from greetings. So the results coming from greetings was around 70K, 90K, something like that. Probably 90K. The one with the stream was 70K requests per second. All these examples that I made tend to transform and process nearly the same amount of information. So in terms of bytes, cents are not that different, because if not, you can't compare the requests per second. No? If you are moving 1 megabyte for each message. Okay, so now CPU usage tells something already, so we are already pushing a bit hard. The number of requests per seconds are nearly the hello world, and it makes sense, no? Because the hello world is returning back a kind of static information. This one is not completely static. It changes every second, but you made a lot of requests in 1 second. So it's definitely very similar, and as it should be, actually. And let's look at the flame graph. And before the pause and after the break, and before the rest, we are going to delete all the HTML because they are accumulating. Okay, again, number of sample. We expect 4K. 4K, 3.9, so it's definitely worthy. If we search for cached, go up, 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 up. Again, like hello, somewhere over the rainbow. It's very tiny because it's a constant value, okay? We can, for example, run the wall clock profiling. I invite you to do it. And if you do it with -E wall, you will see our scheduled time service that sometimes ask for the external service to respond. Because it's idle and it's awaiting to perform that call. So it makes sense that it's going to appear. But we won't do it. Let's take a break. For 5 minutes now? 10? If you want, I can keep on the whole day. Yeah.
other tests. But I'm unable to run it on the Mac. The script, no. I have to have something installed. No, Hyperflow.
I was able to run a couple of scripts.
Yeah.
Maybe
Maybe I need
it's an
to
Intel one, it's not an M1, so I don't know if there might be some incompatibility with M1.
because it tries to download Hyperflow, but it actually gives an error on the JVM.
If you want to, we can have a look at it.
Yeah. Maybe it's trying to download the does it try to download the JVM?
It uses Maven wrapper, so definitely it's going to try to download the JVM.
It works on my M1. I can.
Yeah?
Okay.
It
Yeah.
works, huh?
Yeah. It works. Slightly different results.
Sure, there is
but-
no
The samples are very different.
yeah, right. And I don't even use the same JVM distribution and the
Yeah,
same.
throw this.
There is something that I didn't mention, scare too much people, but one of the other problems is that sometimes the debug symbol of the JDK are broken in specific JDK version.
Really?
Yes, and you observe stacks that never
Try
happen.
The default is the 17.
Why is doing like that? I never
the
do.
Oracle of NGDK.
And that's why
I need to
it's
check.
important
It's
to debate
using
that profile, just
Because I tried
Yeah.
the GK.
adopted
Could be.
Yeah.
JDK, that now
It's sad, but that's why if you are a developer, it's better. Because you have a broad idea.
I have a
What's
bunch of
going
them.
on. If it doesn't
I never
match,
know which one is
someone
it.
is fine.
Yes. Yes. That's good. I like the tooling. I think I'm going to be able to reuse that. That benchmark script is
No, it's nice. You can replace it with whatever you want.
exactly, yeah.
It's actually using Taming 17.7. Apparently.
We
An M1.
Yeah, but I asked him about the which
I
version.
think the problem is the AP loader. You can download the new version of AP loader that has been compiled for F1. That's the problem.
Yeah, but
The AP loader, I just got the one from the
That's
repo.
other funny stuff. You can happen with that one.
Oh yeah.
I got
Depends on the GDK version. Now it captured the signal. It's a sack of things. And that's why I think the people, it's good to be used as a developer. You can go to school. This specific profile. It's wonderful, but unless you are very expert, you risk that it breaks in production.
Oh, yeah.
Yeah, and that's why Datadog made a very good version instead that could be used for real, for containers. And it doesn't break. Because there are a couple of friends working with Datadog,
yeah.
and they have a lot of customers running 24 hours a day.
Yes.
Profiling, they have Datadog.
Yes. They can't afford to.
Okay.
Yeah, you can't afford to break things in production. But if you do it with your local task because you would like to improve things,
Yeah, yeah.
I mean, if it breaks,
It's fine.
It's fine.
not a problem.
And,
It's just crashing.
and you always learn something. Right?
Yes.
Troubleshooting is essentially one of the most
I think that my friend is.
Yeah, it's working now with 17.4.
So it depends. Yeah,
Oh,
it's
no.
No. it happened the same.
No. I must have some property. I wonder if I have some property. No, it started well, has some numbers, but then, but it,
Breaks, but
Yeah, I mean, we can try to update also the AP loader.
so try to update to the latest AP loader.
If you go
Search
in the
GitHub,
README, there is
AP loader.
no, but in the README it's also
Yeah.
explained that you can download from JDK to something, if I remember, because we have one in the repo. It's not literally
It's not the last
version.
up,
Yeah.
up to date.
Worked on mine. But I use Liberica as
Okay.
a distribution, so might be a slight.
I think that even if I don't like to say that, I'm using Oracle because of the debug symbol and say SDK. So I wasn't a great fan of SDK, but
Right.
recently I'm switching with a
Yeah,
very different type of JDKs. And when it happens, I found it quite good. But the problem is how you can tell how to install debug symbol on the
Yeah.
specific JDK. They are not in SDK mode.
Yeah.
So you can use DNF, for example,
Okay.
with the debug info installer and get it for the same minor that you have installed
Right.
in SDK.
Right.
And if you are lucky,
They
the
match.
profiler will pick it,
Yeah.
even if they are not in the right folder, because there is a common shared folder for them.
I see.
And they are going to use that.
I see.
But it's a kind of cheating profiler. The idea is to have a JDK version that got the bugs.
Yeah.
And as far as I know, Oracle till the 17 on SDK man got the version that got the bugs. So you take it, it works. Sometimes there are problems. At least they're there.
I know. I don't know. We ship with.
It's not a problem for CPU. It's a problem for allocation. Because allocation profiling are using completely different mechanism to collect allocation of data.
Yeah.
And these mechanisms make use of the bug information.
All right. And so if you don't have it, you just can't.
You won't see anything. You basically see just on top stack frame with the name of the class without any stack. You see.
Yeah. Okay. I see.
So there is something broken always. It is what it is.
How much content do you have left for the session?
I think is another case, full case, and then opens question. It probably is, given that it's the second time I'm doing it, I'm running faster.
Yeah, way faster. Last time.
When was the first time?
Over TC, no? Boxer TC. Second time in Greece. In Greece it was lower, I can tell you, but it's super fun.
Okay.
Yes, because there is Mario Fosco.
Yes.
He's a great okay. I'm not a great English speaker, but he's definitely worse.
Oh, really?
His accent is pretty strong.
Believe me, it's very Napolitan kind of accent, even in English. And what's fun is that in Greece they got
he's from Napoli.
Yes, they got the translation of what he's doing in English, because for the Greece people.
It's yeah.
And the artificial intelligence wasn't able to understand what he's saying. So he was saying, blah, 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 blah,
Oh, well, but
and then erase.
no, but to be honest, that type of tools are pretty bad. I don't know if you ever tried this feature of Google Meet. It's very bad. I mean, definitely I'm not a perfect speaker, but it probably missed half of the word. So it could be also partially problem of the tool. That's for sure.
I can just say that I was there and it took me a lot of time to stay poker faced. You don't have to laugh. It's not hard. It's not nice, but it was definitely fun.
Yeah, it's running.
It's running.
No segment fault, nothing.
The new version of.
It's just a no. Just another. I tried another JDK version.
Okay, so he's a JDK guy.
Yeah.
Because this guy, the sub guy, has changed the SYNGAT code trace to work for its laptop. That is no, I'm not joking. What's funny is that in the old JDK test suite, there is a single test that whole, and it's used by 25 years.
25.
It's 25 from the first day that Java exists. They open up that API for Solaris systems. It was another of their profiler about
Right.
something at that time. And what's fun is that it's not tested. You can report the garbage data and no one knows. And that's the story of profiling in Java. And when the people told me, yeah, it's a scientific process, there is no test for that. It's not scientific. You should understand the scientific whole process. But the tool itself is just useful. It could be broken. You won't know that until it breaks. But if you know that, at least you are not scared. You say, okay. Come on.
I'm gonna drink some water.
Very happy. The version it should be Because it's so if you try to follow what Sana is typing and you go fast, it's breaking. I should put it in the readme because I just say it by word and it's fast and quick.
So downloading I prefer it's written down. Il y avait aussi beaucoup d'anglais.
First example is WRK. I love the benchmark. Because it's really WRK. But yes.
But that's not what you
It's not what I present. No, the readme should be updated. And probably I will merge it with another project because I was working with the grad team last and I made things similar but could work for native and they are adding part of native. That would be nice because in other conferences the people say, yes, they talk about native, but how do I define it? Is a whole but the data is similar-ish, it's not that different. The tool is different. It's a sax even. Let's go to the list. Remove all the HTML and then I'm going to announce. No, okay. We are going to start in a few. I should go out and shout, hey, come back, don't run away. So it should be not list reversal, but allocation. And we start with random sequence resource, and we move to fast random system resource. Okay. Let's wait just 20 seconds and see. And for who has tried the script and day breaks on M1, it's a JDK version thing. So you can try it out another JDK version. It won't breaks anymore. Another minor of 17 probably. And for who other has run it and it doesn't run, because hyperfoil got in the name of the folder the version, you should remove it. So it's just hyperfoil if you need to try it. I'm going to update the README, but PRs are welcome. So if you need, send it one. If you have any other question so far or what we have observed, please raise it. You can ask pretty much everything related. Yes, please.
You say at the moment that with the Mac we've got a different plane graph. Can you explain again why?
Yes, yes, definitely. So the default behavior for CPU profiling by using a Linux platform is to making use of two things to collect the sampling. One are the async get call trace thing that collect the Java side. But then you have the kernel side. And that kernel side instead is collected by using perf events. Perf events of perf map open, so the call to collect that perf events is not available in Mac. And that means that in theory, and you can't get that information. Is that bad? You have just a slightly limited visibility of things. And Async Profiler is using another POSIX methods to arm a signal handler. They have a timer, and they collect data by using this iTimer thing. They have another problem because of iTimer, because iTimer have a slightly broken kind of behavior when you have too many threads. So you can get a slightly less number of samples than the one you expect. But generally speaking, for laptop-like of experiment, it still works fine. So you shouldn't get an highly different number of samples, in theory. Obviously, if the most of your samples are spent in a stack trace that could be seen only on the kernel, you won't see it, because it doesn't exist for the profiler. Okay, so we can move to another example. So this one, it's so far we have talking about configuration error, about logging error, about biased, about streams, about, and we are still talking about a kind of bias, and bias of mine about streams. So this one, sadly, is coming from another real work example. Obviously, make it synthetic for the workshop, but it's definitely real. So we were having, what's going on? Okay, we were having a method in memory, so an endpoint defined as non-blocking, again, that was using an in-memory database. It was my case. It wasn't an actually in-memory, it was a LMDB, but something similar. And the API of the high-level client of this thing was using stream, because stream are convenient, are composable, are great. But at the same time, this random service that is just producing a CVS-like list of random numbers, so it's very simple. And it is not producing a huge number of numbers, because it's configurable by the parameter. So we will call it with 10, that is fairly low as a number. So in number of bytes, it could be 100 bytes, probably less. And it's not using JSON, it's using text. So it's not even translated in JSON. So it's very simple. But what's doing? It's returning through generate an int stream in the number we want. We are boxing them, translating in stream, and joining through a joiner that is using the comma. It's a one-liner, beautiful. In general, I scared as hell by things like that. So it's too simple. It probably is going to create a string, the box at the type. It's using some intermediate collection to collect this one, and then creating another string to get the delimiter version in. So I usually dislike this kind of things. And I should, maybe I'm wrong. So, but given that I feel myself as a very smart developer, I won't trust this code. We won't even profile it. It sucks. And we will move to another endpoint that is better, because it's pooling. Pooling is great. I mean, you can avoid to have intermediate allocation of strings. And this one is making use of a very smart utils that I made called string builder pool. It's a real story. Probably I made it myself, something like that. And what I'm doing is, oh, it's strange what idea is doing here. Okay, it's a string builder type. Because of var, you can replace var with string builder, and idea won't try to help you. Maybe. String builder, no, it can't work. We need an API. It's a string builder, yes. And now it's more verbose, so thanks idea. Anyway, we are using this pool to acquire a temporary string builder that is thread local, super cool, super fast. We don't need to allocate it every time, no? If you haven't used yet thread local, don't use them. Probably they will break with Loom anyway, so it's not a good idea. But in this case, I was feeling very cool, I use it. And in this way, I could just ask a random service to provide me an integer every time. So it's not even boxed, it's a primitive. This thing should be super fast, definitely. And then, right at the end, I use the string builder that is pulled to return the string. So what I'm allocating is just the string. Because if another call arrives and is being issued on the IO event loop thread is using the thread local, that is local to the event loop thread, to return a pooled instance of this thing. So you shouldn't allocate basically anything about a string. Will be super fast, I'm sure of it. Let's run it. So let's check the name of the resource because I don't remember that. Is the fast random. So you should never name something fast. That's my personal advice, because most of the time it happens, it's probably worse than the original one. So lower your expectation, make it a slow random generator. Now let's see if we have made a good job out of it. Okay, what we know for sure is that we are spending a lot of CPU. That's for sure. And now, still remember our baseline is an 100 bytes string. Is not using JSON. We know that the hello world things was around 90%, 90K requests per second. I won't expect anything better. But how bad can be? What can go wrong? Typical. 61, not that bad, actually. So it seems I made a good job. I don't even need to profile it. Or maybe I would do it. Okay. What we know so far is that there is something wrong down there to the very bottom. Ooh, bad. Type array class, mem allocator, mem set. Ooh. It's yellow. So it's coming from the runtime of Java. And how many samples we got here? Is 10% of one CPU. Twice. It's quite a lot. And it's coming from this event loop thread. That's a broken thing, actually. So believe me, it's broken, the stack trace. But if you won't believe me, you can issue, you can fill an issue directly on a SIM profiler. It shouldn't be there, this thing. But let's say that is right. Still exists. It's saying something. There is some allocation. But we try hard to avoid allocation. What can be wrong? Let's go to the top. Click to the relevant part. And we have our acquire that is just keep on creating things. So as I pitch you, Quarkus is very light, is not doing anything, but calling fast comma separated random int, our instance, and then we keep on allocating string builder. So probably I made a mistake, I make it wrong. Let's take a look at the actual implementation of it. It is pretty bad, okay? And this call stack trace is broken because that part that you see in the bottom should be on top. I don't know why they are not collected. But at the same time, it belongs to the right thread, at least. But anyway, let's look at what pool does. It's our util, so I can look at the code actually. It's not something provided by the JDK. So I'm checking if I'm on the IO event loop thread. So I made it right. So I'm validating that I'm on the event loop thread. I use builder pool, that probably is a thread local. And if, okay. And if it's null, I create and return a new one. Okay. Probably is not releasing it. It just keep on acquiring. So it's just acquiring a new string builder, but then right after, when you have finished with it, you should release it back to the pool. Because if you don't release it back to the pool, there is nothing. And the next time, you should keep on creating it. So let's try to fix this and see if it changes the performance. So it's try finally. We should do a try finally because we really want to release it every time. And the finally should be right after the acquire. If not, you won't have the temp. Exactly. I know, with not UK keyboard, it's a mess, sorry, son. Okay, release. How many people has saw something like that in their life? Lucky you. Okay. Sometimes you have two kind of staged method to acquire, borrow, and release resources. You made things you believe they are faster. You forget a part of it. You won't test it because it's definitely, for sure, better. And you will find out a problem like that. We will use this chance to better study another aspect, so the allocation profile of this application. But right now I would like to focus on what will change in that code when we are going to do the right thing. So, Sanne, did you delete the previous one or is still there? No, just curious, without stopping, just perfect. Perfect, because we have observed that there is a problem. So we have some allocate somewhere. So someone is complaining about allocation. Exactly is the zeroing behind the allocation. It's not the actual allocation, but it's something related to allocation. And we knew that there is a cost. But if you look at the peak performance, even if it was a broken code, the performance wasn't that bad actually. It was 60K thing. No. That means that effectively, unless you should measure to see if GC is a problem. Because here we know that it spends actual CPU time, so it can be a problem. But by looking at the quality of service, 60-something K messages per second was actually very good, still with the bug. I'm not saying to not fix things like that. I'm saying that you should evaluate if they are worthy your time, even if there are bugs. So in this case, I can't see anymore the memset thing that is performed on the allocation. And I can't see anymore the string builder thing. And if I search for the name of the repository, that I don't remember, as usual, the resource, sorry, you will see that something is going on here. What's going on? Let's look at here. We are appending on a string builder that already exists, and we are translating from an integer in a way to put it. And when we perform the acquire to the pool here, if you click here, you will see what happened. So what happened is that we are using thread local to obtain an entry of the existing string builder allocation instance, and we just using it. In terms of percentage of CPU usage, first you can see anymore the allocate weirdo that we got before. That's a good news. And what are the requests per seconds? I didn't check it, actually. Was the final one, 90. No. It's definitely improved from 60 to 90. But how much was the hello word? 90-ish. Okay. I definitely decided up front that the solution that we use is stream was bad. Why we can't profile it and see what are the expected level of performance if they are below? So I'm doing that kind of things that the people tends to say, okay, stream are bad, I won't use it because I measured before. No, you should validate. It is. For this thing is a problem. We are already looking at the amount of CPU time required for that specific thing by using a stream builder is very tiny. So if we are going to run the same experiment, but for the endpoint that we have decided that wasn't worthy, so was just random, we will see which one is faster. And then we can stick for the one that got maybe a better code or maintenance. Personally, I don't like the stream because I probably told 20 times during this presentation. But the thing is that they are builders of things, DSL. And I don't like the fact that I can't relate with the code, what's going on. But at the same time, from the point of view of code maintainability, they are actually pretty better than the thing that I've done. I even used a new class that should be tested and maintained, that is the pool. And I can tell you that I'm hiding a leak, because when you use a thread local, you risk to leak your class loader. If you don't believe me, ask for it. Search in internet. Thread local, class loader leaks. You will find a problem in Spring, as usual. No, it's bad, what I've said is not usual, but it happens. And they have fixed recently in part of their code this thing by using thread local remove. So we are going to add remove to our code that completely defeat the fact that we would like to pull, and probably doesn't matter that it's not a good idea to pull in general. No, because if you do remove, you remove the entry, so you don't have to pull anything. So it's not a good idea, actually. Let's see what, okay. It's like 4%, 5% of different. So it's 86K requests per second. You don't know that, but I can tell you. I've installed the CPU frequency tool, and I'm capping the minimal and the maximum hertz for the CPU. I removed the C state, so I made a few things in order to have slightly more stable results, even if I'm not pinning the running application to specific core. It's stable-ish. So if you have a slightly slower performance, it's likely that is lower performance. If you run it by your own, unless you are navigating or having conference call while during the benchmark, you still get this level of performance, so slightly slower than before. And look together at the flame graph. So, yes? We can try. I mean, the point is that we are is a playground, so we can modify it and see what happened. But it's important the context. So the profiler won't tell you how much is good the practice, but how much is good the practice in experiment and a specific environment. So the kind of information we got so far is that the percentage of CPU, let's say that I can tell you already that the number of samples total are right. But if we search to the top, great. You will see, if you compare with the other one, the global number of samples to be like 131 for two different threads. If we can open the other one, we can see for a specific core, so here, exactly, how much was 64. So we have slightly more number of samples for slightly less throughput. These are two information, very important. It's not just the number of samples, that you should care about, but the peak throughput as well. Because if you perform twice the amount of work, even if you spend more time doing something, it's expected. I mean, you are doing double the amount of work. So you should always consider to use the expected level, the outcome of performance to weight what are your samples, the percentage of your samples. So in this case, we can tell that is slightly more costly, even probably double. But if we look at the percentage, we know that if we are so good, this one is not the new one, is the new one, right? Go to the other tab. If we go here and we look at the percentage in the bottom right of the old flame graph, go bottom right, so you can remove the zoom. Search for that point, that resource. Perfect. It's 3.40%. If we are so good to completely remove that cost, it's very unlikely that you will get more than 5% improvement in this specific scenario. It's not actually true, because if you search for equal weight, we are still not maxing out the clients. So it means that clients, in theory, can do a bit more. So it means that your application, what's doing is a bit more important than what it appears. But given that is a very tiny amount, probably it won't matter. My point is that in a situation like this, I will choose for code maintenance. I don't have to care about resources that are not released. It's less error prone. Yes, it's slightly less readable, but if I have to change it, it's a one-liner and already exists. Why I should rewrite it is not a good idea, even if I completely against stream. No. So this is an important thing. Now, let's see another way to look at the previous problem. Okay, so let's break again. If you can revert back the one with the string builder, I would like to show you another type of profiling data. So as I told you, in theory, we are focusing on CPU profiling, but it's not obviously the only one. There is another one that I found it pretty useful, but you should think up front if what you're looking at is important or not. Because in the current state of affair, when you have fixed both, GC was important? No. From the CPU time perspective, it wasn't even present. So what if I remove all the allocation? Who cares? It's not important. You won't get any benefit, because the point of view is that it wasn't the bottleneck of that application. That's what the profiling data tells you, especially when they're able to show up even GC data. If not, use the GC events, better than GC logs. I strongly invite you to use JFR GC events. They are much more actionable. If you can't, GC logs, be sure that's the problem, okay? Now, we have break it again. If we run this same endpoint, but with -e alloc, it's going to use another thing. Probably, in general, I finished the workshop here, so I don't have to do the allocation part. So I'm doing now for the first time. And in theory, should be worthy to a whole slide. But I will tell you by heart, and if you have any question, just raise it. So the GC mechanism, if you are going to profile what happened from the allocation point of view, it would be super costly. You allocate all the time. Java seems designed to allocate, even entire libraries. So if you're really going to perform sampling of allocation events all day time, it will slow down too much, the application. In order to make it more lightweight, there are few changes coming from Datadog. There are existing behavior from the way by which specific events are emitted that represent the two types of allocation events that we are going to see in our flame graph. If you run it to fast random, minus E alloc. So in this case, what we are going to observe, we have two kinds of events. How many of you has heard about thread local allocation buffers? Okay, very few. That's good. It's better, actually. So what's the point of a workshop? Come on. Okay. So the GC have different implementation that try hard to make allocation to be as cheap as possible. The cheaper way to perform allocation are the so-called bumper point allocation. It means that it's like you have a giant buffer, you have a pointer that tells you that's where I am. I would like to allocate 10 bytes. I will give you that. So it will move the pointer and will give you the memory back. That's the faster possible way to allocate. In order to perform that kind of allocation, this allocation requires to have a staged thing per thread called thread local allocation buffer. They are sized dynamically until certain ergonomics by the JVM, so the GC algorithm itself. But you can think that if you stay within this very special allocation zone, you have allocations that are super cheap. And these allocations, when they are collected, because GC run and try hard to recycle memory to give it back to your application, when it happens, if they are fast enough to give it back, they will give it back to the thread allocation buffer. And then you keep on reusing thread local allocation data. So allocation will be definitely cheap. Is not anything similar to native allocator in C++, on Rust, or whatever. GC are fabulous if you stay within the thread local allocation. What's the point of this explanation? Because the kind of events that we care about and we can collect with in a more lightweight way are events of within a thread local allocation and outside the thread local allocation. So if you stay within the thread local allocation, even if you have a lot of samples, so a lot of new thread allocation within the thread local, is never a bad thing. So it happens, okay? But when you go out of a thread local allocation, could be pretty bad, because what happens if you can't allocate of your local thread? You should go on a shared part that is shared with other threads, and they will compete to obtain the memory they really want. In terms of usage, it will be more usage. It's a contended thing, and these are important events. It means that when it happens, that you go outside thread allocation, probably it's a kind of allocation thing that you will see in the GC logs. Probably you are allocating too much of a smaller thing, or too much of a very big thing that are so-called humongous allocation. They always happen outside of thread locals. So, very nice. It's missing the JDK debug symbol of JDK 17, but it was working before. Okay, I will show up why you shouldn't trust about Profiler. So I update this morning with the, that's always a bad idea, with SDK man to a minor version of JDK 17 and of Oracle. And Oracle tends to have debug symbols in. Why should I care? Because allocation profiling, differently from CPU profiling, require debug symbol in order to present the stacks. So if you don't have the debug symbol installed, and how you can obtain it, DNF debug info install specific JDK version. If you have a Fedora, CentOS, whatever. No, CentOS is dying. I can, right, but anyway, you need to provide those debug symbol, because what you will get is just this. It's not wrong, actually. It's still presenting good data, but the real data is the full stack. While here we have only the top. So sadly, I can present you the allocation flame graph. I can tell you how they are, actually, if you have strong imagination. So in the very top, if you look at it, and you can click it, actually, you have the type of a class of data. And the color aqua are within allocation, within TLAB allocated stuff. So the type of allocation here are the event loop thread as allocated byte array. And if it's aqua, it's good. If it's orange, it's outside of TLAB. And when it happens, it's a good idea to look at the stack trace, okay? So what you will get in the real world is the full stack. But as I told you, the meaning is still there. For the most, I can see only aqua stuff here, and green, but never orange. So probably, as we might know, GC wasn't a problem of that application. And that's the reason why, even with the broken code, the performance wasn't that bad. I was using CPU time in order to perform cleaning up of memory allocated. But the GC wasn't under stress about it. And it was always able to make use of thread local allocation buffer. And the reason for that, you can see it in the throughput, wasn't that bad. Maybe it were to fix it. In that case, yes, definitely was a one-liner. It's a workshop. You have to fix it. In the real world, you can decide. So the allocation flame graph are there to help about it. Done. Okay, 1 minute of question.
Again, coming back to the example on the Mac, using a different JVM, I didn't have at all the issue that showed between the fast R&D and the quick R&D, or the, yeah. Actually, I had the same TPS. Any idea why?
That's a good question. I believe the problem is the operation used to perform the cleaning up of the memory. So in this case, you have even the same performance.
Yeah, exactly the same.
You have M1?
Yes.
Okay. No, but do you rebuild? Okay, no, that's, I mean, can I? Okay. I can tell you my educated guess. So in the stack trace, we will see memset, AVX memset. AVX doesn't exist on M1. Are vectorized unit that are used to speed up operation like cleaning up the memory or copying. So when you perform string system array copy, under the hood, if you have an x86 CPU, very likely you would like them to use vectorized unit that are meant to copy big stuff in 2 different positions. And when you want to clean up something, because remember, as a Java application, when I require memory, I would like it to be cleaned up. No, it's not actually always true, but the idea is that in theory, that's what you want. So in theory, you should find the best way to clean it up, those memory. What's the best way? By using vectorized unit. So my educated guess is that, given that he's using a different method, a different intrinsic to perform that cleaning up, that it's probably making use of the vectorized unit of M1, this is not appearing because of problem of the stack trace of the profiler, because it will be kernel code, very likely. Maybe not. It's an educated guess. What I would do in the real world, I distill a JMH benchmark out of it, and I use the perfam ASM profiler. And I will look at the assembly. Because the name of the vectorized operation on different CPU have a very clear name. So it's just searching for them. If you find it, probably you get a problem on the stack trace because of that one. Sometimes it happens. So the magic of macOS. No, it's not a problem. M1 is wonderful, actually. I have the fun that are running by 20 minutes, actually. So I won't get it with M1. Okay, any other question? Yes, we can do it offline, right.